Welcome to waiting times for Poisson-distributed events. In this video, we're going to look at the waiting times for Poisson-distributed events. For example, let's say we have a radioactive sample that has, on average, 3 decays per minute. What is the probability that we have to wait more than 30 seconds for the next decay? And what is the average time that we'll have to wait for the next decay? In this video, we'll show how we answer questions like these. Okay, so let's talk a little bit about what you'll need for this video. Here, we'll be assuming that you're familiar with the Poisson distribution. If you'd like to know in what situations the Poisson distribution arises, you can check out the video, Why the Poisson Distribution is Important, It's Everywhere, available on this channel. We derived the Poisson distribution from first principles in the video, The Poisson Distribution, Derivation. Although the math here will be less involved, the logic used in that video will be somewhat similar to what we do here. So you may want to watch that video before continuing here. There are also a couple of mathematical relations that we'll need. First, we'll need to know the value of the following infinite series. So the sum of n times x raised to the power of n from n equals 0 to infinity is equal to x over 1 minus x squared. And that formula is valid as long as the absolute value of x is less than 1. For now, we'll take this as given. It is derived at the end of the video after the summary. Okay, we'll also need to know that e raised to the power of x is approximately equal to 1 plus x for the case where the absolute value of x is much less than 1. Okay, with those preliminaries out of the way, let's get started. Okay, so first let's very briefly review the Poisson distribution. The Poisson distribution describes situations where an event occurs randomly but has a constant probability of happening per unit time. We'll denote this probability of occurring per unit time as R. For the example of a radioactive sample given in the introduction, there were on average 3 decays per minute. So in this case, R is equal to 3 per minute. We can ask, given a time interval of length t, for the probability of having n events in that interval. For example, in the radioactive decay case, we could ask for the probability of having 7 decays in 2 minutes. Then we would set t equal to 2 minutes and n equal to 7. The answer to this question is the Poisson distribution. So the probability to have n events given the rate r and the time interval t is equal to rt raised to the power of n e to the minus rt divided by n factorial. And we should note that in other videos we sometimes call the quantity rt lambda. Here we're going to look at some type of event that happens according to a Poisson distribution at a rate r and ask how long we have to wait for the next event to happen. So say we watch some phenomenon that has Poisson distributed events. We observe the events as they occur. For example, in the case of the radioactive sample, the events would be the individual atoms decaying. we define a certain point in time as t equals 0, and we want to ask questions about how long we have to wait after t equals 0 for the next event to happen. We'll call this the waiting time, and we'll denote it as t wait. Specifically, we'll ask 3 questions. Question 1. What is the probability that we will have to wait at least a time t for the next event? For example, we could ask, what is the probability we'll have to wait more than 5 minutes? Or in other words, what is the probability that t wait is greater than 5 minutes? Question 2. What is the probability that we'll have to wait for a time between t and t plus delta t? For example, we could ask, what is the probability that we'll have to wait between 5 and 6 minutes? Or in other words, what is the probability that t wait will be between 5 and 6 minutes? And finally, question 3. What is the average time that we will have to wait for the next event? We'll denote that as t wait in brackets. Okay, we'll start with question 1. What's the probability we'll have to wait at least a time t for the next event? This is the same as the probability of having 0 events in the time t. We'll call this P of t wait greater than t. From our Poisson distribution formula, we see that the probability to have 0 events in a given time interval of length t is given by P of 0 given r and t, which equals rt raised to the power of 0 e to the minus rt divided by 0 factorial. And that's just equal to e to the minus rt. So the answer to question 1 is that the probability that t wait will be greater than t is equal to e to the minus rt. Okay, now for question 2. What is the probability that the waiting time t wait will be at least t, but less than t plus delta t? We'll denote this as P of t wait between t and t plus delta t. To answer this, we'll use the result we just obtained. We obtained the result that the probability that t wait was greater than t was equal to e to the minus rt. Similarly, the probability that the waiting time will be at least t plus delta t is equal to e to the minus r t plus delta t. So, if we want the probability that the waiting time for the next event is at least t, but less than t plus delta t, we can take the difference between these two quantities. So the probability that t wait is between t and t plus delta t is equal to e to the minus rt minus e to the minus r t plus delta t. And that's just equal to e to the minus rt times 1 minus e to the minus r delta t. So that's the general answer to question 2. Of particular interest, though, is the case where delta t is small and r delta t is much, much less than 1. So let's look at that case specifically. For the case where delta t is small and r delta t is much, much less than 1, e to the minus r delta t is approximately equal to 1 minus r delta t. So this gives, for the case where r delta t is much, much less than 1, that the probability that t weight falls between t and t plus delta t is approximately equal to e to the minus rt times r delta t. We also could have gotten this latter result by taking the probability that t weight is greater than t and multiplying it by the probability to have an event in the interval delta t, which for r delta t much less than 1 is approximately r delta t. And note that if we take the probability for t weight to be between t and t plus delta t, and we divide it by delta t, we get approximately re to the minus rt. This expression gives us the probability per unit time of the waiting time for the next event being around t. Okay, finally, let's get to question 3. What is the average time that we will have to wait for the next event? So the average value of t weight. In other words, if we repeated this exercise many, many times, each time measuring t weight, what is the average of the results that we'd get? To compute the average wait time, so the mean value of t weight, we'll consider all possible values of t weight from 0 to infinity. We will divide this range of t weight into thin slices. Each of these slices will be of a duration that we'll call delta t. We will take r delta t to be much, much less than 1. As the slices are thin, the mean value of t weight will be very close to the following. It will be very close to the sum over the slices, which we give the index n, of p of n times t weight of n. Here, p of n is the probability that the next event will happen in slice n, and t weight of n is the waiting time at slice n. We'll compute this sum and then take the limit where delta t goes to 0. Taking that limit will give us the exact answer. Okay, let's start by numbering the slices. We'll number the slices starting with n equals 0. This way, the amount of time that has passed at the beginning of the nth slice is n times delta t. The probability that t weight will fall in the nth slice is the probability that t weight is between n delta t and n delta t plus delta t. And that's approximately equal to e to the minus r n delta t times r delta t. Meanwhile, the value of t weight in slice n varies from n delta t at the beginning of the slice to n plus 1 delta t at the end of the slice. As delta t is small, these values are not very different. We'll take t weight in slice n to be n delta t. We could take it to be some other value between n delta t and n plus 1 delta t, for example, as the midpoint of the slice at n plus 1/2 times delta t. If we took another value, we'd still get the same result after we take the limit delta t goes to 0 at the end of the calculation. We won't show that here, but we encourage you to check that on your own. Okay, so now we have the pieces we need for the sum that we wrote down earlier, which was that the average value of t weight was approximately equal to the sum over the slices n of p of n times t weight of n. So this becomes the sum from n equals 0 to infinity of p of n, which was e to the minus r n delta t, r delta t, times t weight of n, which was n delta t. And this just equals r delta t squared times the sum over n from 0 to infinity of e to the minus r n delta t times n. Okay, so we have that expression from the previous slide. Let's note that e to the minus r n delta t is equal to e to the minus r delta t raised to the n power. So we can use our relation from the beginning of the video, where the sum over n from 0 to infinity of n x to the n is equal to x divided by 1 minus x squared. Okay, so using the value of that infinite sum on our expression for the mean value of t weight yields that the mean value of t weight is approximately equal to r delta t squared times e to the minus r delta t divided by 1 minus e to the minus r delta t squared. Okay, so we have that expression from the previous slide. Now let's take the limit where the slice duration delta t goes to 0. So for delta t going to 0, e to the minus r delta t goes to 1 minus r delta t. We'll just keep the leading order in delta t. So the numerator, e to the minus r delta t, just goes to 1, and the denominator, 1 minus e to the minus r delta t squared, goes to r delta t squared. Okay, so the expression that we had for the mean value of t weight that was written in terms of these exponentials now simplifies down to r delta t squared times 1 over r delta t squared in the case that delta t goes to 0. And the factors of delta t cancel out, and that just gives us that the mean value of t weight is equal to 1 over r. And again, I'll point out that after taking this limit, this result is exact. Okay, so we get the answer to question 3. The mean value of t weight is equal to 1 over r. This is the average time that we have to wait for the next event. This is true for any time chosen to be t equals 0. It is even true if we reset the clock to t equals 0 when an event occurs, reflecting that 1 over r is also the average time between events. In fact, we already knew that the average time between events had to be 1 over r. Imagine we look at a Poisson process for a very, very long time t. On average, there will be RT events in the time t. So the amount of time between events will be t divided by RT, which is 1 over R. Now, this may seem paradoxical. If the average time between events is, say, 5 minutes, and right now it has been 2 minutes since the previous event, how can the average time until the next event, t wait, also be 5 minutes? But if 2 minutes have already passed since the most recent event, you already know the interval between the most recent event and the next event will be greater than 2 minutes. And this is not true of an arbitrarily chosen interval. When calculating the average interval between events, we include all intervals, including intervals which are less than 2 minutes long. If we only included intervals that were longer than 2 minutes, the average interval length would be 7 minutes long. So it is all consistent. Okay, let's briefly summarize. Here we've looked at the waiting time for Poisson-distributed events. In particular, we've seen that for Poisson-distributed events occurring, on average, at rate r, the average time until the next event is 1 over r. Now we'll do the derivation of the sum of the infinite series that we used in the video. So keep watching if you'd like to see that. Okay, now let's go back and calculate the value of the infinite series that we used in the main part of the video. So we used the result that the sum over n from n equals 0 to infinity of n times x to the power of n was equal to x over 1 minus x squared. And that's valid as long as the absolute value of x is less than 1. To do this, let's first calculate the value of another infinite series. So let's look at the sum over n from 0 to infinity of just x to the n. That's equal to 1 over 1 minus x, as long as the absolute value of x is less than 1. Okay, so let's start with that second series, the sum over n from 0 to infinity of x to the n. That's equal to 1 plus x squared plus x cubed plus x fourth, etc. Let's call the sum of this series a. This is a convergent series as long as the absolute value of x is less than 1. So we can perform some basic mathematical operations on the sum a. We'll do two things to a. First, we'll subtract 1, and second, we'll divide the result by x. Okay, so we have that a is equal to 1 plus x squared plus x cubed, etc. So a minus 1 is equal to x plus x squared plus x cubed, etc. And a minus 1 divided by x just knocks the power of x down by 1 in the expression, so we get 1 plus x squared plus x cubed, etc. But that's just equal to a. So we have that a minus 1 divided by x is equal to a. We can collect the terms containing a in that expression and move them over to the right-hand side. So we get that minus 1 over x is equal to a minus a over x. And that's just equal to a times 1 minus 1 over x. We can then multiply both sides by minus x, and we get that 1 is equal to a times minus x plus 1. This just gives that a is equal to 1 over 1 minus x. as we claimed a few slides ago. Okay, now let's try to get the series that we actually used in the main part of the video. And we'll call this series B. So B is equal to the sum from n equals 0 to infinity of n times x raised to the power of n. So that's equal to x plus 2x squared plus 3x cubed plus 4x to the fourth, etc. Let's divide that by x and subtract 1. So dividing by x just takes the power of x in each term down by 1, and subtracting 1 gets rid of the first term, because the first term in b was just x, and we divide that by x to get 1. So b over x minus 1 is equal to 2x plus 3x squared plus 4x cubed plus etc. Okay, so now let's take that result and subtract b from it. So we had b over x minus 1 that was equal to 2x plus 3x squared plus 4x cubed, etc. And we're going to subtract b from it. b was x plus 2x squared plus 3x cubed, etc. If we take that difference, we get x plus x squared plus x cubed plus x raised to the fourth power, etc. And that is just equal to x times a, the sum that we saw a few slides ago. So that's just equal to x over 1 minus x. Okay, so now we have that b over x minus 1 minus b is equal to x over 1 minus x. First, we can collect the terms that contain b on the left-hand side and get b times 1 over x minus 1 minus 1 equals the right-hand side, which is still x over 1 minus x. We can then move that minus 1 from the left-hand side over to the right-hand side and get that b times 1 minus x over x is equal to x over 1 minus x plus 1, which is just equal to 1 over 1 minus x. Okay, so we have that b times 1 minus x over x is equal to 1 over 1 minus x. And that just gives us that b is equal to x over 1 minus x squared, as claimed.